Welcome to the Explainer. Today, we're putting on our lead signal integrity engineer hats. We're going to put aside the marketing fluff, the subjective opinions, and the endless forum debates. Instead, we are going to run a clinical, purely data-driven diagnostic on the actual electrical reality of your signal chain.
So, we've all heard the relentless marketing hype, right? True bypass is the absolute gold standard for preserving your tone. The whole idea is that taking a pedal completely out of the circuit keeps your signal perfectly pure. But we really need to ask a highly critical question here. Is this true bypass architecture actually causing the exact high-frequency signal degradation you are so desperately trying to avoid?
Here is our diagnostic roadmap for today. We'll start with the high impedance trap, move on to the capacitor myth, tackle the true bypass fallacy, look at some hard spectral evidence, and wrap things up with the buffer solution. Let's dive right in.
Part 1. The high impedance trap.
To strip away the guitar player mythology and just look at this clinically, we really have to define impedance. Put simply, it's just the resistance to the flow of alternating current. Because of how they're constructed, passive guitar pickups are high impedance sources. In engineering terms, this means they output a seriously weak signal that struggles big time to drive over long electrical distances.
And this brilliantly illustrates the blueprint of our source. Looking at this equivalent circuit model, you can see a pickup isn't just a simple wire. It actually acts as an inductor, denoted by that L. Because of this inductance, as the frequency of your signal goes up, meaning, the higher notes and those sparkling harmonics, the impedance of the pickup increases right along with it. This creates a really tricky scenario where your high-frequency clarity is highly susceptible to loss before it even leaves the guitar.
So the crucial takeaway here is this stark physical contrast. On one side, our pickup is a fragile, high-impedance source. It's super easily loaded down and extremely sensitive to its environment. But on the flip side, what we actually need to drive a signal cleanly to an amplifier is a low-impedance output. We need something robust, powerful, and capable of pushing that AC wave down long lengths of cable without losing all those beautiful high-end details. Our signal desperately needs a transformation to survive the trip.
Moving on to Part 2, the capacitor myth.
A lot of players think a guitar cable is just a dumb, inert pipe that moves sound from point A to point B. It absolutely isn't. Physically speaking, anytime you have two electrical conductors separated by an insulator, you've created a capacitor. In your standard instrument cable, the central signal conductor and the outer metal shielding are separated by a plastic or rubber insulator, so your entire cable is literally a giant, elongated capacitor.
Let's think of this cable as a leaky tunnel. As your weak, high-impedance signal travels down this tunnel, it constantly interacts with the cable's capacitance. Capacitors naturally store electrical charge, but here's the kicker. As frequency rises, capacitance increasingly shorts out the signal. Your high-frequency particles are literally bleeding out through the walls of the tunnel straight to ground. This acts as a low-pass filter, pulling down the resonant peak of your pickup and basically just dulling your tone.
Which brings us to a major system failure in Part 3, the true bypass fallacy.
Take a really close look at this setup. When you turn off a true bypass pedal, a mechanical switch completely removes the pedal circuitry from the path. It physically hardwires the input jack straight to the output jack. The unintended consequence of this? You have just mechanically combined the length of the cable entering the pedal and the cable leaving the pedal into one massive, unbroken, completely unbuffered electrical run.
To really grasp the scale of this disaster, let's look at some math done by the legendary audio engineer Pete Cornish. Let's say you use a standard 15-foot cable from your guitar to your board. String together 10 true bypass pedals with 2-foot patch jumpers, and then run a 30-foot cable back to your amp. When all those pedals are bypassed, your weak, fragile pickup is suddenly forced to drive a staggering 63-foot continuous capacitive load. No way around it.
Extending that leaky capacitive tunnel to 63 feet creates a massive, unmitigated load. And as Cornish points out, this absolutely destroys your high-end clarity. It strips away the harmonics and just leaves you with a muddy, muffled signal. You are essentially asking a very weak pump to push water through a very long, very leaky garden hose. It just doesn't work well.
Part 4. Spectral evidence.
Now, we don't have to just guess or rely on our ears here. Let's look at the clinical proof on this right-hand graph. This is an actual frequency sweep from GigFX analyzing these exact bypass methods. Check out that static purple line representing true bypass with two cables connected. It drops off an absolute cliff right around 2 kHz.
It's literally reducing the bandwidth of the guitar by almost half compared to the reference. Now compare that to the electric cyan line, which represents the buffered bypass. It actively preserves those high-frequency harmonics, keeping the signal healthy and bright. It's a night-and-day difference.
This data clearly shows how cumulative cable capacitance just drags your tone down. If we look at the 3 dB high-frequency roll-off point, which is basically the exact moment your treble noticeably starts to die, having no cable keeps it at a pristine 4.76 kHz. Add a 16-foot cable and the leak begins, pulling the roll-off down to 4.38. Push that to a 35-foot unbuffered run, and it plummets to 3.75 kHz. You are visibly and audibly chopping off the top-end sparkle of your instrument.
Finally, Part 5, the buffer solution.
The fix for all of this is actually surprisingly elegant: an active buffer circuit. Notice how the buffer perfectly isolates the input cable from the output cable. Because of this, no matter how many pedals you turn on or off downstream, the guitar's pickup only ever sees that very first short cable run going into the buffer. The capacitive load literally stops accumulating right there.
Here's how this actively rescues your signal health. The buffer basically acts as a signal pump. First, it presents a very high input impedance, usually around 1 megaohm, which perfectly receives that weak signal from the guitar without loading it down at all. Second, the active circuitry converts that signal to a very low output impedance, often around 100 ohms. And finally, it acts as a line driver, safely and powerfully pushing that bright, complete wave through the rest of that 60-plus feet of cable without any further high-frequency bleed.
The absolute beauty of this engineered solution is that you don't need a buffer in every single pedal. Having just one high-quality, well-designed buffer early in your signal chain will essentially shove that sparkling treble and vital signal health through all your subsequent true bypass pedals and massive cable runs. It restores the whole system.
So, we've reviewed the electrical blueprints, we've traced the vulnerabilities, and we've looked at the irrefutable spectral data. And it all leads us to one inescapable conclusion that should totally guide how you build your rig moving forward. Clarity isn't a choice, it's physics. Protect your signal. As we wrap up this diagnostic session, I want to leave you with one final question to think about regarding your own setup. Have you audited your signal chain's true capacitance footprint recently? Or are you, right now, unknowingly letting your high frequencies bleed out in the leaky tunnel of a massive true bypass chain? Think about the physics, grab a buffer, and take control of your signal integrity. Catch you next time.